All right, everyone. Welcome to Active Filter Design E5340. This is the first lecture. I will just introduce the course and give you an overview of what all stuff you will learn in the course. To appreciate the role of active filters, consider the diagram of a generic signal processing system. You have seen this before in the context of where A to D and D to A converters are used in practice, and filters are not too far away from the A to D and D to A converters in the signal chain, right. So, natural signals or analog signals are stuff which are continuous in time and amplitude and occur in a variety of applications, namely whether you are sensing RF signals using an antenna or using sensing acoustic signals using a microphone, whatever. To process these signals, it becomes advantageous to do it in the digital domain for reasons of programmability and changing of processing in the field and so on. So, you want to process this using a DSP. Now, there needs to be some electronics which converts from continuous time, continuous amplitude to discrete time and discrete amplitude, and the role of that is fulfilled by the interface electronics. Now, the interface electronics therefore includes stuff which needs to, one, sampling, right, because you must convert from continuous time to discrete time, and two is quantization. Quantization we have already seen in the ADC class. And so have we seen sampling, right? Sampling and quantization together constitute the analog to digital conversion process, and the reverse happens at the D2A end. Now, what we are interested in is figuring out what to do before sampling, right? We know that whenever you sample a signal, if the sampling rate is not sufficiently high, then there will be aliasing, and therefore there will be a potential loss of information, right. We also saw in the last class, in the last course, that even if there were no signal components beyond Fs by 2, where Fs is the sampling rate, if you didn't do anything, then noise outside the 0 to Fs by 2 band will alias into the 0 to Fs by 2 band, and therefore corrupt or reduce the signal to noise ratio. So, the golden rule therefore is that before you sample, you must have what is called an anti-aliasing filter. The job of this anti-aliasing filter is to remove all frequency components in the signal beyond at least the 0 to Fs by 2 band, right. I mean, it might many times, as we have seen in the oversampling case in the data conversion class, the signal bandwidth can be much smaller than the sampling rate, in which case the specs on the filter get greatly relaxed. But in general, all that you need the filter to do is to remove the so-called anti-alias filter this is the DSP, right. So, the focus of the A to D converter class was this E658 last semester. The focus of this course is going to be the design of filters, and one specific application of a filter is to do anti-aliasing, right. There are several more which will come to as we go along, but the block diagram shown here is intended to illustrate the fact that wherever you need an A to D converter, in principle you need a filter. And since more and more processing is done digitally these days, it thus follows that whenever you do digital processing, you need an A to D converter. Whenever you need an A to D converter, you need a filter, right? So filters are everywhere in electronic systems and also in daily life. Our eye is an optical filter. It only responds to EM waves in a narrow bandwidth, right? 4000 to 7500 angstroms. The ear is an acoustic filter which responds to, I mean, if you're lucky, 20 to 20 kilohertz, 20 hertz to 20 kilohertz. Okay. The mouth is also an acoustic filter, right? It always doesn't filter what you want it to, but right. So it is the D to A conversion process. You understand? So filters are everywhere. The focus of this course is on special kinds of electronic filters, which are called active filters. Right, and the qualifier active is used in opposition to what are called passive filters, right? Because active filters use active elements, namely transistors or combinations of transistors, to realize the filtering function. Okay. Now, the reason why active filters are studied rather than passive filters, which itself is a vast area and very exciting subject on its own right, is that in most electronic systems today, it so happens that the frequencies that we deal with are all in the several tens of kilohertz to several hundreds of megahertz range. Okay. So at these frequencies, making filters using passive elements, which can be done, right? So all it takes to realize a filter is one inductor and one capacitor, right? To realize a second order filter, all that it requires is this. Okay. In fact, you can even do it with two capacitors and two resistors. Okay. You will not get as good a filter you might want, but I am saying that it is very easy to realize filters using passive elements. Then the question is, hey, if you can do it with passive elements, why bother with transistors at all? The reason is the following. I mean, like every filtering process that we know, we want the filter to be, within quotes, good. What are the characteristics of a good filter? I mean, a good filter is one which rejects, or which is very efficient at distinguishing two signals which are supposedly very close, but you want one and you don't want the other, right? You understand? Just like a good examination is one which is supposed to ideally separate students into two distinct groups, one which knows what it's doing and the other one which doesn't, right? But you know that it's impossible to design an examination system like that, correct? Whatever examination system you come up with, you will always find that it's impossible to do this efficiently unless you spend a lot of time doing it in the examination process. The same thing with the filter also, right? If you want a filter which is very frequency selective, then its impulse response will be long. Okay. All right. So in other words, a filter which is very discriminatory in nature is requires, it turns out, as I'll give you intuition later on, that it requires poles whose quality factors are very, very high. And once the quality factor is very high, it turns out that you cannot do it with simply either RC or RL. You need both kinds of elements, both capacitors as well as inductors, in order to realize filter transfer functions which exhibit high degrees of rejection. Right? If the filter is very loose, then most likely in many applications it may not be even useful. Okay. All right. Now, at this point you just take it from me that sharp rejection means high quality factors for the poles, right? And if you want high quality factor, it turns out that you cannot get them with simply either RC or simply RL. You need both L and C and of course R. If only had LC elements, then all the quality factors would be on the j omega axis. It would all be quality factors would all be infinite, right? Okay, which is again something you don't want. You want high quality factors, controlled quality factors. You don't want the quality factor to be moving around when temperature changes or when things age. Okay, so it turns out that you need both L and C as reactive elements as well as R. Now, time constants are all of the form RC, L by R and root LC, correct. So, it thus follows that if you want to realize filters in the low kilohertz to several hundreds of megahertz range, it thus follows that the time constants that will be involved will be, the order of microseconds in the megahertz range to several milliseconds in the kilohertz range. Now, if you want milliseconds of time constant, then if you want to realize a millisecond time constant using only R's and C's, then if you choose for example a kilo ohm, then what will be the time constant that what kind of capacitance will you require to get a microfarad? And you know that a microfarad is it's okay to build discrete circuits using a microfarad, but you know that on an IC for example a microfarad is a complete no-no, simply because the area occupied by the capacitor will be so huge that your transistor will be, whatever else you build will be this small, and then there's this big microfarad capacitor. Okay, the alternate way is to say, okay, I will choose an R which is very big and therefore reduce C. Okay, so and what do you think is the problem associated with increasing R? For example, what I am getting at is that you can realize tau, which is RC, in let's say for example 1 millisecond in many ways. One is to choose R is say 1 ohm and C is 1 millifarad, or choose R is 1 kilo ohm and choose C as 1 microfarad, or choose R as 1 mega ohm and C is 1 nanofarad, right, or any other permutation combination thereof. So the question is, it seems like as I go on increasing R, the capacitance goes on decreasing, isn't it? You can have infinite combinations of resistors and capacitors while all giving you the same time constant. The question is which one to use. If capacitance becomes too big, we know that large capacitance is problematic, then one could argue that the capacitance can go on you can go on reducing capacitance by increasing the resistance. So what is the problem with this argument? It turns out that resistors not only resist but they also add noise. Okay, so those of you who have not done noise, don't worry about it, but it turns out that the larger you make the resistor, the more noisy the filter gets. In other words, the filter whose job is to take a signal, separate it in principle into two components, reject one component, send out the other, is now also adding noise to the whole process, its own noise. Okay, so it's therefore corrupting the wanted signal. So, and it turns out that as R becomes larger, the noise due to the resistor becomes larger and is therefore causing more corruption of the desired signal after filtering. So in practical systems, therefore, it is not possible. The system will simply not allow so much noise to be added, which means that there is a upper limit to the values of the resistors you can use. Yes, sir. Yeah, in the most simple case, it is KT by C noise, right? Because you have RC. We have seen that for a first order RC filter, the mean square noise of the output is KT by C, correct?
That doesn't depend on the resistor.
No, but the bandwidth does depend on the resistor, right? If you want to realize a certain bandwidth, correct? If you want to realize a certain bandwidth, then 1 millisecond, for example, in this particular example, 1 millisecond is fixed. If you do want to get tau is 1 millisecond always, right? Then if you try to increase the resistance, the capacitance will decrease, which means that kT by C for a given bandwidth will keep going up. Does it make sense? Okay. Those of you again who have not seen noise calculations before, don't worry about it. We will get to it later on. At this point, the key point to note is that there is a system imposed upper limit to R, which means lower limit on C. Okay. Further, we also see that only RC or only RL networks do not filter effectively. And why is this? Pardon? So if you have an RC or RL network, all the poles, it turns out, are constrained to lie on the. If you have a network with only R's and C's or only R's and L's, where are the poles of the network constrained to lie? They all will lie on the negative real axis. Why negative? Because by definition it's a stable system, right? And it turns out that RC or RL networks will have poles only on the negative real axis, which means that you cannot get complex conjugate poles, which means that the quality factors of the poles you can get is very small, which means that you cannot generate frequency responses which are very sharp and discriminatory in nature, which is what constitutes a good filter. Is this clear? Okay. So you therefore need L, C and R needed useful filters, and if time constants are low, okay, then L becomes very large. I'll make an example. Let's say you want a time constant of 1 millisecond corresponding to say about a kilohertz, a pole at a kilohertz, right? Actually this is smaller than a kilohertz, but I just take this as an example, right? This must be square root LC. Okay, the pole frequency must be a function of L square root LC, RC or L by R, and if I choose C to be a nanofarad, then what is L? Ten power minus 6 divided by 10 power minus 9, which is, sorry, is a millihenry or square root, sorry, 10 power minus 6 divided by 10 power minus 9, sorry, oops. Okay. All right. So as you can see, the amounts of inductance required are too large to be practical. I mean, 1 Henry of inductance is a lot of inductance. 1000 Henries is an impractically large amount of inductance. Okay. Yeah, these time constants are high. I mean, it's a reasonable thing to assume because for example, see, a lot of this active filter work was motivated by telephony, right. So, in the early 60s and 70s, when people were trying to build telephone networks across America, right, digital telephony, right, that is where all this PCM, GCM stuff started happening. Then they had to digitize voice, right. So, they had, the first thing to do was to take voice, limit it with a 3 kilohertz filter, because all the useful stuff that you say is all there in 0 to 3 kilohertz. And then digitize it, and then do all this PCM and then muxing and switching and all that stuff, right. So, and then they realized that, hey, if you want to build a 3 kilohertz filter, you need oodles of inductance and capacitance in order to get poles that at such low frequencies. Okay. Now, 3 kilohertz is therefore a very reasonable frequency to work with. All that I am pointing out is that 1 millisecond is not an impractical time constant to realize. Of course, of course, now we also have applications which go down to several millihertz. For example, a lot of biomedical signal acquisition, right? Stuff in our body happens at few hertz, correct? So, if whenever you are trying to acquire biopotentials, there is a big interferer in terms of the 50 hertz that is floating around, or 60 hertz if you are in other parts of the world, floating around everywhere. You are trying to acquire 20 microvolts from say an EEG pickup, and you run a cable to the machine, and now the cable, it's not inconceivable that it picks up a few millivolts of 50 hertz noise. You need to get rid of that, right? Which basically means that one way of doing this would be, in the good old days, would be to put an analog filter which would get rid of the 50 hertz. So, now you have to have a corner frequency which is of the order of several tens of hertz. Okay. Today, of course, you can simply sample at a much higher rate and then do everything digitally, right. But this is one more application area where time constants can be extremely large, with necessitating passive elements whose values tend to become very, very large, right. And this is also an active area of research. People are trying to figure out how can I make large time constants in as small a physical space as possible. Okay. So, this example is just to illustrate. What happened now? This example is intended to illustrate the magnitude of the problem, which is, it is very difficult to realize the kinds of inductors required for applications where the time constants are within quotes small, right, a few milliseconds to several microseconds, even several tens of nanoseconds, will still put the pole frequencies in the several hundreds of megahertz range. Okay. And it turns out, therefore, that on-chip inductors are a possibility, but they are only limited to on a chip. In principle, there are metal layers used to connect transistors, one transistor to another, and you can always wind it up as a spiral and then create an inductor. You understand? Making an inductor is very straightforward. Take a wire and coil it up, you will get a lot of inductance. In fact, even a regular wire will give you inductance, but if you coil it up, you will get more inductance. Okay. So, but on chip, if you don't want to waste most of the area of the chip making spirals, an accepted maximum of a few tens of nanohenries perhaps is the absolute limit beyond which the inductor becomes so big that it becomes commercially unviable to use them. Okay. So, given that you can only realize tens of nanohenries, it becomes impractical to attempt to build filters unless the frequencies that you are talking about are several gigahertz. Okay. So, then people started thinking about the problem, which is, hey, great people from the 1920s onwards all the way up to the 1950s figured out the following, which is given a filter a filter characteristic I want, okay, how would I approximate this by a ratio of polynomials in S? Okay, that has been worked out. That's simply a math problem, correct? So why are we worried about ratio of polynomials in S? Okay, so let's stop for a minute and think about why this is important. Why do you think, what is so special about the ratio of polynomials? Do you understand the question? Figure out how to approximate a desired magnitude characteristic as a ratio of polynomials in S, so that they could realize them using lumped elements, namely inductors, capacitors and resistors. Okay, once you have a polynomial in S, the job doesn't stop there. We need to figure out an LCR network which gives you this ratio of polynomials as a transfer function, right? So this whole area is what is called network synthesis. Or more correctly, passive network synthesis, where what people tried to do was try and figure out ways in which one can realize a given transfer function using passive elements only, R, L and C. Okay, and these are now extremely mature fields, and by the time the 50s and 60s were there, people had figured out pretty much what to do and how best to do it. All right, that is and both these areas are very mathematical. We will get a flavor for this as we go along this course. But in the early 60s, when the active filter guys came along, they found that all this stuff was very nice, right? However, the inductor values you get become too large to be practical. Okay. Now, if things become too large to be practical, you have to do something to figure, you definitely won't be able to implement it on an IC. And telephony was a big application at that time, so people were trying to figure out what to do. And then, at the same time, that's about the time when transistors and op amps started becoming commercially available on a large scale with prices which some people could afford. Okay, then people start saying, hey, what can I do if I now bring in transistors into the picture? Is it possible that I can get rid of the inductor, correct, and somehow use a combination of transistors, capacitors and resistors to realize transfer functions whose qualities, whose quality factors are very high. Okay, in principle, it seems like it should be doable, right? Okay, because an active element, incrementally, behaves as if it's giving out power, isn't it? If you simply take a transistor and do its, you find the total power it puts out, total absolute power it puts out cannot be, greater than 0 because it's drawing power from the supply, right? But it is incrementally active in the sense that if you look at only increments, then it can be made to look like an element which seems to be supplying power to a network. If now you have elements which start supplying power, then in principle you can put the poles anywhere, right? You can put the poles even in the right half plane, because the right half plane, why is a passive network restricted to have poles in the left half plane? It can't generate power on its own, correct? Now that restriction is removed. So in principle, though we don't know how to do it just yet, it seems that using active elements R and C, one must be able to put poles anywhere, which means that you can get arbitrarily sharp filters, okay, using only transistors, resistors and capacitors. And commercially this is extremely important, because transistors are very, very tiny, okay. Another way of looking at it is the following. If you kind of stare at a capacitor and an inductor, a capacitor, what is the relationship between the voltage and the current? Vc is 1 over C integral IC dt. Okay. Let me get rid of the subscript C and C here. In other words, the voltage across a capacitor is the integral of the current. On the other hand, an inductor the current is, how can you write the current in terms of the voltage in an inductor? Is 1 by L integral V dt. Okay. So what do you notice here? There is something that strikes you. Pardon? So you can see that both an inductor and a capacitor are fundamentally doing the job of integration, right? The capacitor is integrating current and giving you a voltage, an inductor is integrating voltage and giving you a current. So one idle thought that strikes you is that if I took an inductor, right, and put a box in front, the magic box here, okay. So this is I2, this is V2, correct? And this, if I put a magic box here which somehow converts the integrator, the inductor current, okay, that is I2 here, into voltage, and converts the integrator, the inductor voltage into a current, right? Then an inductor can be made to look like a capacitor. By the same token, if I took the same magic box and put a capacitor here, and the magic box, what is it doing? The magic box is taking the voltage at port 2 and making it look like the current at port 1, and taking the current in port 2 and making it look like the voltage in port 1. In other words, it's interchanging the role of voltage and current in the second port. Okay. Once you have a magic box like this, then to realize an inductor, all you have to do is you take this magic box, put a capacitor on the other end, look like an inductor at this end. Now you have an inductor, now build whatever you want with this inductor, right? So the fundamental idea is to realize that if you take a capacitor and interchange the roles of voltage and current, then in principle you can get an inductor, sorry. Okay, and what is this, what is this interchange the role of voltage and current? In other words, you want a port 1 current to be dependent on port 2 voltage. So in other words, this is a current which is dependent on a voltage. So this is a voltage controlled current source, right? So so this leads us to the idea of, hey, if I had controlled sources, then I can make a capacitor look like an inductor or vice versa. The reverse thing is not useful in practice, but in principle there is nothing wrong with it. I can make an inductor look like a capacitor also. If I had the same magic box, and it seems like the magic box must only consist of controlled sources, because it's converting voltage into current and current into voltage. It's possible to do this using controlled sources, and based on all our transistor level design courses, we know that a transistor operating in the active region behaves like a the basic incremental transistor model is a voltage controlled current source, and by connecting it up in various ways you can realize all the four basic current control sources: CCCS, CCVS, VCCS, and whatever the other one is, right? You understand? So this therefore means that even though you don't know it as yet, it must be possible to use transistors, bipolar, MOS, JFET, whatever, right, to realize an incremental, realize a box which will interchange the roles of voltage and current, and therefore get rid of this problem of inductors. Okay, and now once you know this, then that's it, right? You just put once you know this trick, it's just a matter of now synthesizing all the filters that you want. Okay, so this is one approach to doing active filters, and one of the first approaches to do this, right? And so therefore this whole active filter design in the beginning was motivated by the fact of trying to reduce the size of the inductors. All right, and as you can see, it is heavily based on all the prior work, which is approximation, right, and network synthesis, and thanks to the work of all these great guys, you have a passive network whose magnitude response approximates to a close degree what you want, and then thanks to the transistors we are able to replace the inductors with a combination of transistors, resistors, and capacitors, which gets rid of the size problem, right? And all this together makes an active filter. Okay, and like most things in life, there's nothing free. The moment you add transistors, what happens? A transistor is A, noisy, and B, nonlinear, unlike an inductor or a capacitor, these are ideally linear elements, right? So the moment transistors are there, you have extra sources of noise, and distortion from the active elements. Okay, so the moment you start talking about active filters, obviously we'll have to understand how noise and distortion affect the performance. Okay, and this is just one way of trying to reduce or eliminate the inductors from the equation. Okay, it's not inconceivable that there are other ways of also realizing high quality pole pairs, okay, without doing this inductance replacement method, right? There are many ways of doing the same thing, and each of them will lead to a family of filters. Okay, and like everything else, there's it's not that there's one silver bullet solution to everything, right? Some things are good for some applications while not good for others, and vice versa. Does it make sense? Okay, so this is the whole So we now not only have to worry about what topologies to use once active elements are brought in, we also need to figure out how exactly to design the active elements. It turns out that using op amps one can do it. It turns out using control sources one can do it. We'll have to obviously figure out which is a better, smarter way of doing things. Okay. Then we've come through this far. We'd like we've built designed our filter. The next thing is to actually test the filter, right? You've designed the filter. It's an integrated filter. You've done the layout. You send it for fab. The chip comes back, and we need to figure out how to test the filter, right? So this is what you call a crucial and a practical issue which we need to figure out. Okay. So this course will take you through the entire process, starting from approximation. Right, and the four important characteristics that we'll try to approximate, right, which are useful in practice are: we'd like to build an ideal. What is this? What kind of filter is this? Low pass filter. We'd like to build what is this? An ideal band pass filter. What is this? This is a high pass filter, and this is a band stop filter. Okay, and clearly, by the very nature of these pictures, it's apparent that no physical network will be able to realize something where no physical system will be able to realize anything where anything is differentiated with respect to anything else will give you a step, right? Everything will have finite slope. So none of these characteristics are realizable in practice. They can only be approximated to an arbitrarily closed degree. Okay, so approximation is the art of finding, or the science of finding, a ratio of polynomials in S which approximates any one of these curves in some optimal fashion. All right. So we will start with low pass because this is most widely used. Okay. Once we spend some time figuring out how to approximate a low pass ideal brick wall, then it turns out that if you have done all the hard work, it seems kind of visually apparent that if you spent a lot of time figuring this out, then perhaps, what is this? It is the same thing moved this way, right? So it seems, at least, you wait for another 10 minutes. Okay. So I lost what I was saying. What was I saying? Yeah. So the band pass is simply the low pass moved this way. So it seems conceivable that you don't have to redo the entire math for the band pass separately. It seems as if we should be able to exploit all the hard work that we have put in when we did the low pass filters. Just looking at the similarity between the characteristics. One can be gotten from the other by moving stuff around and so on. So it turns out that that's indeed true. Once we have a good approximation to a low pass filter, you can generate equally good approximations for the band pass, the high pass, and the band stop filters with minimal effort. You don't have to go through the whole approximation process all over again. You understand? So these come under what are called frequency transformations okay, all right. And let me also add the following. This as I say, right, this approximation lies in the eyes of the beholder, right. So one person may say this is a good approximation, another person may say this is a good approximation. We all know that we can't get the ideal step anyway, right. So everybody is right in his or her own way, right, which means therefore that since you cannot get the ideal, if you could get the ideal then there is no quarrel, right, but we know that you cannot get the ideal. So how close one gets to the ideal, this definition of close is now up for grabs, right. Each one may claim that his is closer to that in some sense. One example is of two things being close together is in mean square sense, right. So you find the difference between the ideal and the actual and do the square of the error and integrate from 0 to infinity, and that gives you one measure of the difference between the two. Another person may come and say, oh, that doesn't make sense to me. What makes sense to me is the absolute error between the desired and the actual, and not just the absolute error, the maximum value of the absolute error, right. So and I'm going to work out the math to go and figure out how to keep that absolute error the minimum. That need not necessarily leave me with a solution which is whose error is small in the least square sense. So all that I'm trying to point out therefore is that there are many ways of doing this, right, which therefore means that there are many approximations in practice. In other words, there are many ways of deriving a ratio of polynomials which will approximate the ideal brick wall in some sense, optimal to the originator of that approximation. I will discuss some popular, commonly used approximations. I am sure many of you have heard of what are called Butterworth